Today, in the series of lectures on miscellaneous topics, I will be talking on temperature measurements. You know, the objective of the furnace is to heat the raw materials at a particular temperature, and this temperature is a very important for certain refining, heating, sintering operations or whatever metallurgical object is for which the metallurgical furnace is being employed. What I wanted to convey, that measurement of temperature is one of the very critical area, and the technology of measurement of temperature under very adverse condition, it has to be done. With the adverse condition, I mean, say for example, take a fuel fired furnace where the temperature is very high. How we are going to measure the temperature? In liquids, the flow is turbulent, the gases are evolving. So, under these adverse conditions, we have to measure the temperature, because control of temperature is also very important from reaction point of view. So, let us see about the temperature measurement. You know, I do not think we can measure temperature directly. What we have to do? We have to measure a change in property with the temperature, and ultimately that has to be calibrated in terms of the temperature. For example, expansion of the fluid. If it is a function of temperature, we must know how the temperature is varying the expansion of the fluid. Or for example, resistance of the wire, if it is a function of temperature. Then for various temperatures, we determine the resistance, and from resistance we back calculate or we back relate with the temperature or radiation to that extent. So, that means the temperature is rather measured indirectly from the response of the change in some property with the temperature. So, accordingly, the temperature measurement at high temperature, measurement at high temperature, it is done one by the thermocouple and second by pyrometer. These are the two technologies for measurement of temperatures at higher temperature. I am not addressing to the thermometers which are used for relatively very low temperature, for example, boiling point of water or 200 degree plus and so on. I am addressing the issues where we are measuring the temperature of the order 700, 800, 1000 or 1400 or 1600 degrees Celsius. So, it is in that reference the technologies which are available for measurement of temperature is thermocouple and pyrometer. Thermocouple is based on the measurement of temperature by thermocouple is based on thermoelectric phenomena. Based on thermoelectric phenomena. Whereas, the principle of measurement of temperature through pyrometer, it is based on radiation. Based on radiation. So, let us take first of all thermocouple. Now, it is well known that when two dissimilar metals are joined together, an electromotive force is established. So, our problem is solved of measurement of temperature. We take two dissimilar wire, we join them, put that bead or that joint at high temperature, we can measure the change in the world. So, we got the technology of measurement of the temperature. That means, all that we require to measure the temperature by thermocouple is to search two dissimilar metals and join them. In fact, the fundamental principle lying this technology is the Seebeck effect, which probably you must be aware from your knowledge of physics. So, the Seebeck effect can be easily illustrated. For example, I take two junctions, the one is created by one type of wire and another by another type of wire. Say, let us take it, this is wire B, this is wire A, and this is T1, or let us say T1, which is hot junction, and this one, let us take it T2, this is cold junction. This is cold junction. Now, in between these two, if I put an indicator, it records the EMF. This is an indicator, and I put this indicator and I connect it. So, this is an indicator. Then I will be able to record the EMF produced by this particular thermocouple. In fact, the thermocouple which I have formed is by joining wire A and wire B. So, this is in fact a Seebeck effect, and this E potential difference which is created, that is equal to Ks into T1 minus T2, where Ks that is equal to Seebeck effect or Seebeck coefficient. Seebeck coefficient. So, what you notice from here, that in the measurement of temperature by the use of thermocouple, there is a hot junction and there is a cold junction. So, if you want to employ this technology for the measurement of temperature in a furnace, say let us take for example, this is a furnace, this is a furnace, octane, this is an enclosure, this is a furnace which is for example maintained at temperature T1, and I took a thermocouple produced by one type of wire here and another wire is here, and I make a sort of a joint, and then I connect it through an indicator. This is an indicator, and then here what I do, so in fact now this is the wire A, wire B, and this whole I call it to be a thermocouple. This one is a junction box, that is there I have connected both the leads of the thermocouple. In fact, this is the both these they form a thermocouple, and this one is a cold junction compensation. This is a cold junction compensation, and this is an indicator. This is an indicator, and these, let me put the rating. So, this one they are the compensating leads. Compensating leads. So you note that in order to measure the temperature of the furnace, which is a T1, I have taken a thermocouple, I have inserted it, then I made a junction box, and the another end should be cold junction. So in between hot and cold junction, I will be reading a temperature or a potential difference which will be correlated with the temperature. So the requirements for just such a measurement, the requirements for the thermocouple, the first requirement is that the thermocouple material its melting point, of course, thermocouple's material melting point, it must be greater than measuring temperature. Measuring temperature. Now it's very simple. When you insert a thermocouple, it's a metallic wire, so it should not melt. Melting point should be higher than what you are measuring. Second important thing, that because you are choosing two dissimilar material, so better would be if those dissimilar material would able to generate large value of EMF for a small change in temperature, then the accuracy will be higher. Say if you are able to generate a large EMF with a small increment in temperature, then the accuracy will be higher. The second important thing is that the dissimilar the material or thermocouple material should generate large EMF with change in temperature or with temperature. That is the second important requirement. This is from the accuracy point of view. Third, as far as possible, EMF versus temperature relationship should be linear. To the extent possible. Now, why this is required? Again, I repeatedly am telling you, the output of thermocouple is not temperature. The output of thermocouple is EMF, that is in volt. So what you will be doing? You will be taking a thermocouple, you will put in different temperatures, and you will record the value of temperature, and corresponding to that temperature you will record the volt. So you get a relation, or you get the values of volt against temperature. Then for an unknown situation, you will insert that thermocouple. If then you read the EMF value or the volt value, then you go back to your data and hit that particular volt, and you say this is the temperature. So remember, the output of a thermocouple is not temperature, is the volt. That means you are indirectly measuring the temperature of the object or of the furnace. So for that purpose, it is the calibration of the thermocouple is a very important issue. How we are going to calibrate the thermocouple? We will come back to a little late. So now the different materials, the materials for thermocouple, there are two types. One based on noble metals, say for example platinum and platinum, rhodium, and like this, and another material, they are base metals. They are base metals for example, copper, nickel, manganese, chromium and iron. Now, I will give you some important thermocouples which are frequently used with their composition, temperature range and maximum temperature range. So, I will make a table for you. On the say international standard, the thermocouples are classified by a letter B, E, J, K, N, R, S and T. So, accordingly I am going to write. So, the type of thermocouples, I will make a table, type of thermocouples. See, I will put first of all designation, then the positive wire and then the negative wire, then normal temperature range, normal temperature range and maximum temperature range, maximum temperature range, and here I will put name of thermocouple, name. So, first of all let us take the designation. For example, one is B, and B, the positive wire is say platinum 70, rhodium 30, 70% platinum, 30% rhodium. Negative wire is platinum 94, rhodium 6, normal temperature range 871 to 1705. This is I am putting in degree Celsius, this is also in degree Celsius. Maximum temperature range is 1750 degrees Celsius, and this thermocouple is called say platinum rhodium thermocouple. Another designation is say E. E is having nickel 90, chromium 10, and here nickel 45 and copper 55. You know this composition is called constantan. This one, and the range, normal temperature range, it can be measured 0 to 800 degrees Celsius. Maximum temperature range is 850 degrees Celsius. So, this thermocouple is chromal constantan thermocouple. Constantan thermocouple. Third type of the classification is J, where the positive wire is iron. Here is same nickel 45 and copper 55. The normal temperature range is 0 to 700 degrees Celsius. You can measure up to 760 degrees Celsius, and this thermocouple is called iron constantan thermocouple. Constantan thermocouple. Then here K, in which positive wire is nickel 90, chromium 10, negative wire is nickel 95, manganese 2, aluminum 2 and silicon 1, can go up to 1200 degrees Celsius, and maximum you can go up to 1260 degrees Celsius, and this all of us know this is called chromal alumal thermocouple. Then we have another which is called N. This is nickel 84.5, chromium 14 and silicon 1.5. Negative wire is nickel 95.5, silicon 1.5, manganese 0.4, can also go up to 1200 degrees Celsius, is 1260 degree, and the name of the thermocouple is nitrosyl nicyl. So that is what this thing. And then you have R. In the R we have, say, platinum 87, rhodium 13, platinum can go up to 1500 degrees Celsius, maximum is say 1700 degrees Celsius, and the thermocouple is known platinum rhodium thermocouple. Then again we have one more variety, that is S, which is platinum 90, rhodium 10. Platinum is the negative wire, it can go up to 1480 degrees Celsius, maximum is 1700, and it is also named platinum rhodium thermocouple. So these are the say type of thermocouple which you can get in the market. And of the common, you must have heard the name of chromal aluminal or platinum rhodium thermocouple. Platinum rhodium thermocouple is a bit expensive. Chromal aluminal is widely used. Now, say one of the important thing is the calibration of the thermocouple. So calibration of thermocouple is done by using some of the standard temperatures of some of the elements. For one of the say by using say boiling point of oxygen. The boiling point of oxygen is at a fixed temperature, and that is equal to minus 182.97 degrees Celsius. So one can calibrate the thermocouple against the boiling point of oxygen, or one can also calibrate the thermocouple against boiling point of water. Boiling point of water, which is equal to 100 degrees Celsius, or one can also calibrate thermocouple by measuring temperature of solidification of silver or gold. The respective melting points are 960.8 degrees Celsius and 1063 degrees Celsius. So this is how the calibration is done. Now, one of the most important thing that we have seen in case of measurement of temperature by thermocouple is there are two junctions are involved. One is hot junction and another is the cold junction. Normally, the cold junction should be at 0 degrees Celsius, because what tables of EMF against temperature which are being created, they are created by taking the cold junction to be at 0 degree temperature, because what voltage difference you are recording the voltage difference between hot junction and cold junction. So cold junction is also to be standardized, and for all standard condition the cold junction should be maintained at 0 degrees Celsius. For any other temperature, accordingly correction is to be employed, and that is very important. So, and in this way I will go for cold junction compensation. Cold junction compensation. Now, we consider that we are putting a cold junction at certain non-zero temperature, for example T2. Let us say the hot junction temperature, let us take it T1, and cold junction temperature, let us take it T2, then E measured, that will be equal to Ks into T1 minus T2, because you are measuring the voltage across the two junctions. One is a hot junction, another is a cold junction. Now, the standard EMF tables in the standard EMF tables, T2 is taken equal to 0. These tables are prepared by considering T2 equal to 0. So, E standard, that you will get equal to Ks into T1 minus T0, where T0 is maintained at 0 degree Celsius. So, with the condition that your T1 minus T0 is greater than T1 minus T2. So, the indicator will record less value of EMF because your cold junction temperature is other than 0 degree Celsius. So, accordingly, we have to make a cold junction compensation. If we do not do the cold junction compensation, then accordingly our temperature measurement will have certain amount of error, and that error will correspond to the difference in temperature from 0 to the temperature of the cold junction. So, that is an important. There are devices or there are designs to rectify the source of error in temperature measurement, and these are called the cold junction compensation. So, the cold junction compensation method, cold junction compensation, that can be done by several ways. One of the way that I am listing, for example, we have got the EMF value, and from EMF we have noted down the temperature, and to that temperature we add the environmental temperature. So, one method is that add environment, add environmental temperature to the indicator value, to indicator value. This is one way. Another way, little bit sophisticated way, that indicator needle is connected to a bimetallic spring. That means use of bimetallic spring. Bimetallic spring. That means indicator needle is connected to a bimetallic spring which expands or contracts depending on the changes in the environmental temperature. So, as such you are recording the value after correction of the cold junction temperature, because you have now bimetallic springs and they expand or contract depending on the temperature. This is another way. Third way is that the use of thermistors in thermocouple circuit. In thermocouple circuits. So, this is how you are going to do the cold junction compensation. Now, remember, this cold junction compensation is a very important issue. Now, in this connection it is also important because you are connecting the thermocouple wire, and from thermocouple wire you are going to the indicator. So, some wire you will be using out. So, they are called also compensating wires. Compensating wires. Now, normally these compensating wires should have the same, should be the same EMF as that of the thermocouple wire, otherwise you will again record a wrong value. So, normally they are color coded, say in fact red color for all negative wires, whereas the positive wire, say for a thermocouple J type it is white, for thermocouple K type it is yellow. In the previous table I listed J, K and all. For T type it is blue, for E type it is purple, and for N type it is orange. So, accordingly these wires should be used. Then the another important thing is the selection of thermocouple. Selection of thermocouple. There are so many different types of thermocouples are available. So the selection criteria of selection, one, whether you are having batch furnace or continuous furnace. Batch or continuous furnace. This is one such, that whether batch wise, that means whether you are measuring the temperature in a batch, or in a continuous you are measuring the temperature. That is one important thing. Another important thing is type of atmosphere. Type of atmosphere. Because in the previous lecture, which was on the atmosphere, you have seen that there are oxidizing atmosphere, reducing atmosphere, neutral atmosphere. For neutral there is no problem, but for oxidizing and neutral atmosphere, one has to be careful about the selection of the thermocouple. Third important criteria of selection is the response with change in temperature. Response with change in temperature. Now here it is important that you select a thermocouple which gives little large variation in the volt when the temperature is changed. So these are the important thing. Another important is the insulating tubes. Because you are not putting the thermocouple bare into the furnace. You are inserting in a insulating tube, and normally these insulating tubes are twin hole ceramic tube, and into the twin hole you put in one hole the positive wire and another hole you put a negative wire, and at one end of the wire both the wires are joined by, and that joint is called a bead, that is the solder joint, and then rest of it is connected to the indicator and so on. So normally the insulating material, that is called sheath, and the sheath, various sheath materials are say sillimanite, mullite, that can be used up to 1550 degrees Celsius. Then you have silica alumina, that can go up to 1600 degrees Celsius. Then you have silicon carbide, it can also go up to 1650 degrees Celsius, and fire clay, of course it can't go above 1100 degrees Celsius, safe is 1050 degrees Celsius. So these are the some of the important issues in case of thermocouple measurement. Now one of the important thing is that when we measure the temperature of gas with the help of thermocouples, I will address this issue, because in many situations when the gases are flowing, you want to know what is the temperature of the gas. So it is also important the gas velocity. The heat will transfer by convection and radiation to the thermocouple bead. The thermocouple will also radiate depending on the wall temperature of the duct. So as such, the measurement of gas temperature with the help of thermocouple. Now consider, say this is the furnace, and the gas is flowing, and we have put a thermocouple. This is the bed of the thermocouple. These are the wires. So this is the thermocouple. This is the wall, is at some temperature, and gas is also flowing at certain temperature. Now the principal heat flow involved, the gas is also at some temperature. Let us put the temperature of the gas is T gas, temperature of the wall is T wall, and T couple, that is the temperature of thermocouple. Temperature of thermocouple. Right? Now, the principal heat flow involved are the principal heat flow involved in this one, say, flow of heat between gas and couple, that is thermocouple. This will be by convection, this will be by convection because the gas is flowing, or by a mechanism of convection plus gas radiation, and this will be controlled by the so called H gas, which is heat transfer coefficient. H gas is the heat transfer coefficient from gas to the couple. This is what the heat flow that involved is one, this one, and second, as the sheath of the thermocouple also gets heated up, it will also radiate its heat. So, the radiation between confining wall and couple, that we will say it is HW, where HW is heat transfer coefficient, from wall to couple thermocouple. Now, at steady state, what will happen? The net heat flow to the couple is 0, right? So, at steady state, net heat flow to the couple is 0. Net heat flow to the couple, I mean it's a thermocouple, is 0, and we can quantify this, say heat transfer from gas to couple, that is T gas minus T couple, that will be equal to HW into T couple minus T wall. Remember here, T gas, T couple and T wall, they are the steady state temperature of gas, thermocouple and wall. So, now error in measuring say gas temperature, that will be equal to T couple minus T gas. If that is equal to 0, then there is no error. So, this is the error which is introduced by this heat transfer mechanism, and this error, if we put this equation, then this error is equal to HW upon H gas into T wall minus T couple. So, we can straight away think of the methods to minimize the error. So, error can be minimized Error can be minimized one by reducing SW, by reducing SW, or by measuring when wall and gas temperature are equal. Then you start to measure the temperature through the thermocouple. Another way is that by increasing H gas. How will you increase the H gas? H gas is the convective heat transfer coefficient. You know the flow is turbulent. If you want to increase the heat transfer coefficient, then you have to increase the velocity of the gas. So, another way is that to increase H gas by increasing, for example, velocity of the gas. Third, we use a fine wire. Fourth, omitting protection tubes. Omitting protection tubes. Fifth, silvering the couple. Silvering the couple to reduce its emissivity. I mean, this will help to reduce emissivity. To reduce emissivity. And sixth, we use radiation shields. Radiation shields. Say, for example, in one of the case, what we can do, this is the furnace. Say we insert a thermocouple. This is the bead of the thermocouple, and these are the wires. And what we do here, this is the gas flow direction, and this one is connected to aspirator or vacuum. This is a shielded high velocity thermocouple suitable for gas temperature measurement. For gas temperature measurement. Here this is the furnace, or this is the duct, or whatever you want to say. So the gas is flowing, it is sucked. So this is the way of say minimizing the error, and this is what I have to say about the thermocouple. Now towards the end, I would like to illustrate you the error that one can make in the temperature measurement, particularly when the hot gases are flowing, then what error you can make and how to minimize those errors. Now, for example, let us consider a problem, say hot flue gas is flowing in a duct, whose internal wall surfaces are at 600 Kelvin. The temperature indicated by thermocouple, by a thermocouple is 800 Kelvin. The convective heat transfer coefficient, from gas to thermocouple is given, say it is 110 watt per meter square Kelvin. Now you have to calculate the error in temperature measurement. That is, you have to calculate Tg minus T couple. If there is no error, then Tg minus T couple should be 0 and Tg is equal to T couple. So let us see. Now this typical heat transfer problem, you know that if we do the heat balance, that is the heat approaching to the thermocouple, heat transfer coefficient A1, that is the area, Tg minus T couple, that should be equal to A1 heat radiation, right, from the thermocouple to the wall or wall to the thermocouple. So A1, F12 is the view factor, epsilon 1 is the emissivity, and sigma is the Stephens-Boltzmann constant, that is T couple upon 100 raised to the power 4 minus T wall upon 100 raised to the power 4. All the values are known to us. Now here, say A1 cancels because the area of the thermocouple is the same. Epsilon 1 is the emissivity of the thermocouple sheath. So epsilon 1, say you take the emissivity of the sheath, let us take equal to 0.7. So Hg is known to you, T couple is given, T wall is also known to you. The T couple is 800, T wall is 600. I mean, you can substitute the values, there is no need for me to substitute. So straight away I go to the answer. So I can see now that the Tg minus T couple, that comes out to be equal to 102.4 Kelvin. So you see, this is the mistake, or this is the error you are making in measuring the temperature of gas by a thermocouple 102 Kelvin. Now suppose you want to minimize the error. Now what I do now, say earlier my steady state wall temperature was 600 Kelvin. Now what I do, I measure when the wall temperature attains 700 Kelvin. So now if steady state wall temperature increases to, let us say, 700 Kelvin, then T wall is become 700, I resubstitute, then I calculate the error, get Tg minus T couple, that is equal to 70 Kelvin. So it is equal to 60 Kelvin. So you see now, one of the method of reduction in the measurement of temperature of gases by thermocouple is to see that the wall temperature should be sufficiently get higher, or other way also you can decrease the temperature by increasing the convective heat transfer coefficient. How you can increase? The convective heat transfer coefficient depending on the velocity, to increase the flow rate. So this is the problem I thought maybe it's very important for high temperature metallurgist, say how to measure the temperature and the correction factor to incorporate in it. Now next thing is as I said, that the temperature can be measured. One way was the thermoelectric phenomena, and the issues related to thermoelectric phenomena I have addressed. Now another method is to measure the radiation, and this is called radiation pyrometry. This is called radiation pyrometry. Now, as all of you know, a body at higher temperatures, it emanates electromagnetic radiation. This is a known fact. And this intensity of radiation, say intensity of radiation is proportional to T to the power 4. This is well known Stephens-Boltzmann's law. Now, the principle of radiation pyrometry, is in fact based on this Stephens-Boltzmann's law. Now, the radiation can be measured directly by a sensor, and this can be compared to the radiation of a body of known temperature. That means, we try to measure, or if we can measure the intensity of radiation emitted by a body, and if we can compare this radiation with the standard body, then we can say this is the temperature of the body. So, this is in fact the principle of radiation pyrometry. That means, we need a system which can see the radiation. We have to design a sensor which can see the radiation, and then it can compare those radiation with the known body of that radiation. So, that is the principle of radiation pyrometry. Another important thing is that radiation pyrometry is a non-contact type of measurement. Non-contact type of temperature measurement. Whereas thermocouple was contact type measurement, because in the thermocouple you insert thermocouple in the sheet, and that thermocouple, it rather immerses either in the gas or in the liquid, or it touches the solid. That means, it is a contact type of temperature measurement, whereas a radiation pyrometry, it is a non-contact type of temperature measurement, and the further principles of the radiation pyrometry I will be discussing in the next lecture.